everybody. My name is Wonsak Daniel Lee. I'm a professor in the Department of Agriculture and Biological Engineering at the University of Florida. We have been working on detecting citrus greening infected trees from 2007 to 2017. So I'd like to share some of our efforts in this presentation. Yeah, I'd like to acknowledge the contributions from many people. A lot of people worked on these projects. Yeah, and you guys all know the HLB is the yellow dragon disease or Huanglongbing. Yeah, and you are familiar with this picture here. The Asian citrus psyllid is the vector and in the lopsided fruit, and the light green and yellowish green canopies. Yeah, so here the earlier in Florida, like these ground the crew inspected the trees and then identify infected trees from the grove, but it takes a lot of time and it's very subjective and labor intensive. So we wanted to implement a remote sensing technique, imaging, aerial imaging, satellite imaging, and also we developed ground-based detection system. Yeah, so let's take a look at the aerial imaging first. So here is the imaging location in 2008, 2007 actually, and the location is southern part of Henry County and about 800 hectares in Valencia Hemliner varieties, and there were about 12,500 infected trees. And here's an example aerial image of the citrus grove, and these X marks are the locations of infected trees. At the time, we counted about 12,500, and compared to the number of total trees, it's about 10%. And we thought that was too high, very high at the time. But now we are talking about 95% infection, so 10% is extremely low at the time. Yeah, and we used ISA Eagle sensor for aerial imaging. Spectral ranges from including visible and near infrared range, about 128 bands. And the spatial resolution of 1 pixel is about 0.7 meter. And this slide shows you the comparison of HLB infected and the zinc deficient and healthy. Healthy is green, zinc deficient is blue. So if you look at so this x-axis is wavelengths from the visible to near infrared range, and we can see clear difference on this green band around 550 nanometer, and then a little bit of difference in this NIR range. Yeah, and then this one also shows you the comparison between healthy in blue and HLB infected in red, and we can see clear difference in this NIR range. And another example spectra of different conditions, healthy and HLB. So for analyzing these images, we implemented spectral angle mapping. This one is to find the similarity by calculating spectral angles between two spectra. And then another method we implemented was spectral feature fitting. That is to compare the shape of the spectra with the reference spectra and using least square technique. Here is an example of detection by spectral angle mapping at SAM. And left side is the infrared image, and the plus sign is HLB infected location. And then the right side is same result. And so what we want here is the plus sign should coincide with the red pixel. Yeah, but we found some ground truthing problem here. So that plus sign, the spectra is in white color in this spectrum, and then the pixel on the left is green spectrum, and then the pixel on the right is red spectrum. So remember the spatial resolution of this image is 0.7 meter. So if you move 0.7 meter to the left or right, you will get a very different spectrum. So that means the ground truthing, accurate ground truthing is really, really important. And then we also tried another aerial imaging using a hyperspectral camera, multispectral camera, and the color camera, like in this slide. And this slide shows you the specification of those cameras. And the example multispectral image of Summerland Grove here. Yeah, and then the example color in the color infrared image. I'm not sure whether you can see, but there are many plus signs that indicating infected tree locations in color on the left, and then infrared image on the right. Yeah, and then again, we collected the average reflected spectra of 6 different classes from those images, and we implemented these different methods: discriminant analysis, mixture tuned matched filtering, and spectral angle mapping, and linear spectral mixing. Yeah, and then this table shows you the detection accuracy. So detection accuracy ranges from as low as 53% here, and then as high as about 86%, depending on the method and also the data set. But here we found that the spectral angle mapping produced better accuracies among all these. We did aerial imaging again, and this slide shows you camera and the calibration tarps, and also ground measurement unit, handheld spectrometer. Yeah, and then this one is also the average spectrum of different classes: healthy, fruit, and HLB, and branches. And this one is average spectrum of multispectral image pixels on the left, and then hyperspectral image pixels on the right. Yeah, there is clear difference between healthy and HLB. Yeah, and then this table shows you the detection result. There are so many different numbers, and we tried the multiple years aerial images and also the different methods. And the red on the line, those are better results. And so here we found that the simpler methods like a Mahalanobis distance or minimum distance showed better detection results. Yeah, and based on that, we were able to create like this density distribution map. Green is low infection, 0 to 70 trees per hectare, and then severe is red, more than 210 trees infected per hectare, using different methods. And we developed the extended SAM method by expanding spectral angle mapping and adding some other processing steps to be more efficient. And here are some example airborne hyperspectral spectra. On the left, that is the green is healthy, red is HLB infected. We can clearly see the difference between the two. And on the right, that is first derivative of those spectra. And we can also find the big difference in the red band, the 700 nanometer. And the detection result is about 64% and 86%, depending on the method that we use. And we also tried UAV, a drone, using those bandpass filters. Yeah, and here is the example map image of left side is aerial image and the right side is drone image. So you can clearly see that the drone image is much better because it has higher spatial resolution. Yeah, and then here also we tried the different methods, and we compared aerial images and the drone images. But as you expected, drone images produced a higher detection accuracy because higher spectral resolution. And we also tried satellite images. We utilized the World View 2 images, and that satellite has 8 spectral bands. And this table shows the wavelength ranges. This is an example image of Southern Garden in Henry County, Florida. Yeah, so if you look at the this part here, and then this is a panchromatic image, and spatial resolution is 0.5 meters, much higher resolution. And then on the right, this one is example multispectral image with spatial resolution of 2 meters. And this slide shows you the data analysis procedure. And here we utilize two different library sets, library 1 and library 2. And here is an example result using minimum distance. So on the left, that is using library 1, we achieved about 72% detection accuracy. Library 2 on the right, we achieved about 78% detection accuracy. And then this graph shows you the summary of all those different methods and comparison of airborne and satellite images. So the line here. So this line shows you the average airborne hyperspectral image detection result. It's about 62%. And then the other one here, the highest one here, satellite multispectral image using library 2, we achieved 76% detection accuracy. So by common sense, we expect the aerial images have higher spectral resolution, and also we expected higher detection accuracy. But in this case, satellite images produced higher detection accuracy. Yeah, and we also developed ground-based sensors. You all know the HLB effect is the trees accumulate the starch. And the starch has a characteristic of rotating light, which means that if you shine the light one direction and then the rotated light is 90 degrees from the original direction. So using that characteristic, we developed the polarized imaging system. And here is the picture of first prototype. And then if you look at this part right here, the white object is the lights, and then the black object is two cameras. And here, if you look at this is the polarized filter, and the direction of this larger part is horizontal, and then this smaller part is vertical. So they are 90 degrees direction, so that we can take images from leaves in two different directions using two cameras. And at the bottom, that's where we put citrus leaf to find whether it's infected or not infected. And then we developed second prototype. We were able to use only one camera. But here we put the polarized filter in front of the camera, the vertical direction, and then the surrounding area, we have illuminations, lights, and then the polarized filters on the horizontal direction. So they are 90 degrees apart. Yeah, and then here's an example of HLB negative that is healthy, and HLB positive that's HLB infected. The first row is color image, and then the second row is the images acquired by our polarized imaging sensor. Yeah, and then we achieved around very high accuracy, around 97% detection accuracy, and we used only two statistical features, and so it was very efficient and accurate. Yeah, and then the most commonly asked question on disease detection is that you should be able to detect as early as possible, right? Because if you can see the symptoms, that means it's already too late, because the tree is already infected. So for that part question, we try to detect as early as possible. So we manually infected citrus seedlings in a screen, in a cage, and then we took images, polarized images. So the top picture is color, and the bottom is polarized image. And then here is again another example of healthy and citrus screening infected leaves, and more examples based on the degree of infection. Yeah, so here we found that we were able to identify pre-symptomatic and early symptomatic leaves, and also we were also able to identify non-symptomatic stage of the disease. But here, because we use the polarized imaging, the distance between camera and different leaves, that caused some problem. But this research showed a very good result, so we can use it for high throughput screening of young citrus plants. Okay, so this is our conclusion. We found that the accuracy of ground truthing is really important, and also we should be able to classify the degree of infection of the trees. And then a higher spatial resolution also worked better, and extend the same method promising results. And also World View 2 satellite images produced good results compared to aerial images, and ground-based sensors worked very well. Okay, that's all I have today. Yeah, thank you.